West Coast early. Happy to see everybody after the weekend. I got two, maybe one from this class about COVID. To be expected. COVID, I teach micro here a lot. COVID has become, well, you're about something with COVID today, so it has evolved or morphed, changed over the years. And basically, it's for the most part, as we're seeing now, a mild, relatively contagious type of flu. So I don't go nuts when you see people with it, because you're in close quarters. Not therein is the problem. Young, healthy individuals, no. Unlike the initial presentation way back in 2020, a little different. You'll get to it if you're with me in micro, which I'm sure I'll teach a section or two. It morphs. RNA viruses are inherently unstable. They keep changing. That's why the quote vaccine doesn't work. Changing. That's what flu vaccines basically don't work. They change. But I digress. Opinion based on fact. Moving on. So without further ado, let's begin. I'm really ending this last PowerPoint just to underscore two slides we didn't do. And that's understand what governs chemical reactions. Rate is certainly significant. Temperature up to a certain point, very significant. And again, it's average kinetic energy of molecules. You increase the number of collisions, okay, of molecules, they come in close proximity. And as you will see, it's based, all biological reactions, with extraordinarily rare exceptions, are based on the presence of fairly large proteins that we'll come to know in this next unit are called enzymes. They make it easier for the reactions to occur without being used up. That's the beauty of enzymes. You can use them and use them. They do it very, very quickly. They can, we'll use the term catalyze. They can impact thousands of reactions in a fraction of a second. That's the, and be able to, it holds them, boom, let's go. Holds them, let's go. Magically, whatever is being assembled or disassembled occurs. Temperature just increases the rate of the reaction up to a point. We said a little bit of temperature is good. That's part of inflammation. And when you get excessively, those enzyme systems, which are proteins, begin to change or lose their shape. And that, unfortunately, makes them less efficient. The same is true if the temperature goes down. Not only are the collisions less likely, those enzymes begin to lose their shape. That's what today's discussion, a lot of it is about pH and temperature. Those are points that it has to work around with a little bit of range of forgiveness. In temperature, we're at 37 degrees Celsius. It's still working. If you have 104 fever, that's 40 degrees Celsius. You're really sick. Most likely you and I would be in a hospital, at least overnight for observation. Those systems are still working, but they're in peril. If they go up another degree Celsius to 105.8, you're in big trouble. I'm not saying it's going to die, but you and I would be in big trouble, for instance. Or the same is true if it went down precipitously. Certainly, up to a certain point, increased kind, the word usually is well placed here. The more reactants, the more stuff you have making those collisions, okay, it's likely going to increase the rate up to a point. And you'll find out that the point means how many available enzymes, are there enough available or enough receptors for the reaction to occur. More on that down the road. And smaller things move faster. So the catalyst increasing the rate without being chemically changed or becoming part of the product. So they just stick around in their native form. And you're going to see it's a shape change when we get down to it. And we call them enzymes, which are biological catalysts. Much of your genetic code makes these enzymes. And that really is the last part of that particular PowerPoint of relevance, which brings us is the frame for understanding the next, which is biochemistry. And biochemistry, just as it states here, fairly straightforward, and we're going to get to the other big factor as well as temperature, and particle size is a little factor, and a concentration is a little factor. The two big players, temperature and what we're going to talk about shortly, pH. Biochemistry is the study of chemical composition of reactions of living matter by them. All chemicals, two groups. They point the exception out later about carbon. Carbon dioxide and carbon monoxide, which have carbon dioxide is a major player in our bodies, and carbon monoxide is a major toxin, by definition, are not organic, even though they have carbon. Because again, it's not carbon to carbon or carbon to hydrogen bonds, period. In the old days, we had a cleaning fluid called carbon tetrachloride. They don't have it now. We had it in our house back in the 50s and 60s. A deadly poison. That's why they don't even make it anymore. Okay, you got a stain on something. You didn't have magical things like we have today. Stain on the carpet, stain on the fabric. You get the carbon. Oh my God, we're breathing that stuff. That, even though it had carbon, even though it was covalently bonded, it was carbon chloride. Yeah, bad news. Organic compounds, okay, containing carbon, again, covalently bonded, and many times with hydrogen. And these are the 4 categories that we'll study. We'll just introduce it likely today. And we'll start with carbohydrates. So we have, and basically you're going to see their construction, with the exception of fats, which are the oddball, have a small molecule. And then when we chain them together, either identical ones or ones that are similar but not quite identical, we get complex molecules or macromolecules. That was the whole introductory nugget in that hierarchy table. So we go from small molecules, and we're going to look at the small carbs, the amino acids, which are the small building blocks of proteins, the nucleotides, which are the building blocks of nucleic acids. And fats are kind of, we just look at them and kind of see how they come together, because they really, again, aren't bonded. They just have a natural tendency to group together. Okay, so, and all of them contain carbon, are usually fairly large, and usually, all the components are going to have some degree of covalent bonding. And yeah, we got to have them. Water. That whole thing with H2O and all the stuff I talked about, particularly those hydrogen bonds, account for these properties. It's very straightforward. Most of us on average are around 75% water. So understanding water's properties and the impact it has, the beauty of water, those hydrogen bonds, we have to impart energy. So before the water molecules can break apart, those hydrogen bonds can absorb the heat when it cools. Okay, by the same token, they can reform and establish greater stability or return to the original molecule. By the same token, it's hard to create those molecules and release them all simultaneously. Vaporization is like making steam. I mean, your bloodstream doesn't steam. If your bloodstream starts to steam, you're going to die. Let's be clear. If somebody gets to a temperature of 108, it's very unlikely they're going to survive. Very unlikely. They become severe hyperthermia. Your enzyme systems start to break down. Your proteins irreversibly change, denature. Eventually, you're frying yourself on the inside. It's just rare cases. Cold is a bit more forgiving. So that's the idea. Capacity for heat and resisting the complete disruption and changing from its liquid state to a gaseous state. The solvent. I'm not going to walk through the aisles again. Enough of that. That only works one time. You got to keep that Yankee insignia up front. It's important. First Yankee game was 64 years ago. Beat the Angels. Yogi homer. Not the bear. Yogi Berra. Not Yogi with Boo Boo. Hello. Hey, Boo Boo. Picnic basket, that guy. No. Oh, the Ranger's going to get you, Yogi. Don't do that. Some of you did watch cartoons when you were little. I went through multiple generations. Now I'm working on yet another generation. Dad, I don't want to watch cartoons. Sit down and watch them. I like them. I'm telling you, that's what I did. You will sit and you will watch them. We have ways of making you watch. Reactivity. Water reacts beautifully because things dissolve into it. They play a vital role, as you're going to see very shortly. Every time we build something in our body, we take away a water. When you build something, it's called synthesis. You make something. When you take away water, it's called dehydration, another name for how we assemble bonds to store energy or make structural material, dehydration synthesis. By the same token, whatever you had to eat or drink today is being broken down in your system by adding water to it. I mean, if it's like me, if it's coffee or a liquid, it has water in it already, so you don't have to worry about it. It'll take water from your system in some way, shape, or form and use it to break down bonds. When we break something, we call it lysis, Lysis. And if you use water, hydrolysis or hydrolysis. We say hydrolysis. Okay? And that's part of its reactivity. And mechanically, they'll show you the example for cushioning. The same thing. It's your central nervous system, brain, and spinal cord are a wonderful thing. Originally, they were a hollow tube filled with fluid or water called cerebrospinal fluid. And you find that the fluid is not only in the middle of the tube, it's on the exterior. Okay, so it contains water in the inside, water on the outside. It's wonderfully buoyant. If you're jumping up and down, doing an activity, doing a sport, it's not like your brain's hitting the top of your head every time you do that. That's kind of what happens with concussions. With rapid change, you can't compensate, and the side of where it's coming from, the brain hits the opposite side if you didn't know. That's kind of how we look for things like that. Nevertheless, okay, it's all about the cushioning, the cerebrospinal fluid. It's remarkable how it can take it and prevents your brain from sinking in, so to speak, that fluid, because it's so heavy comparatively into a structure where the spinal cord starts and exits the skull called, as you will learn in the lab, if you didn't know already, the foramen, big opening, generally circular, magnum implies the largest. A lot of the foramina, which is the plural, have different names based on their shape. Oval, spinosum, rotundum for round, oval for oval. So here's the heat. Absorbs and releases it with little change because of hydrogen bonds. Vaporization. Evaporation requires an enormous amount of heat. And by the same token, it's very useful. So we can take things that are very hot and steamy and they cool down relatively quickly that are there. The solventability is remarkable. Proteins are very large molecules. Why can they dissolve in the bloodstream? Because the water can surround. Typically, the exterior portion of proteins has a lot of water-soluble aspects of their composition called amino acids. They're charged particles, effectively, and they dissolve in water. It's interesting that proteins in their interior and their design is such that they're compatible with fats on the interior. That's why they can move around in our membranes. Because in membranes, they're not tethered or bonded that's why we have the fluid mosaic model when you get to it. When you get to cells, and we talk about cell membranes. It's all about this composition. That's why the biochemistry is important to understand. And yeah, which major transport, here's the water molecules getting around the salt, ionizing it, we did that. Reactivity, hydrolysis, and dehydration synthesis. And I always use the same example whether they have it in text or not. Protects organs from physical trauma. We have a lot of cushioning, and a lot of it's based on water. Certainly the brain and spinal cord, the best of all these examples. So salts dissolve in water. And this is what I was trying to show before. Let me see if I have that still readily available. So up on the board, I take a picture of something. Water, under normal circumstances, water has charge particles. Okay. And what will happen, even if we just had a pinch of salt, and if you get tap water, it has a accumulation of different, what we call salts. But they basically are, if you want to think about it, mineral properties. Different waters have different tastes. But what happens in water will basically, under normal circumstances where they're not an excessive or unusual particles, it will undergo the process of partial ionization of water. That means a very tiny amount. Normally, and it's consistent, normally, 1 times 10 to the minus 7. That means out of 1 molecule of water, of which there are, you see Avogadro's number up there, 6.02 times 10 to the 23rd of those in, slightly more than half an ounce of water. So imagine how tiny they are. 1 out of every 10 million. There's the number. That's 10 to the minus 7. When you have a negative exponent, so if you're using scientific notation, 10 to the 7th would be 10 million. But when we put a negative sign, it doesn't mean it's a negative number. It just goes in the denominator. That's the magic of scientific. You see a lot of scientific for many of you down the road. So why, if one of those, if I have 10 million molecules, one of them ionizes, why should I put a dot? Why is that important? It's important because it's easy to get 10 million of those when basically a half an ounce has more or less 6 times 10 to the 23rd. And if you do the math, what happens when you take that 1 times 10 to the 7th, and that's the number of hydrogen ions, because everything's framed in that, times 6 to the 23rd, you get 6 times 10 to the 16th. That's 6 times 1,000 times a trillion. That's a lot of charged particles in a half a tablespoon, or half an ounce rather, basically a tablespoon of water. That's a lot of charged particles. That's very significant. That's why a lot of the chemistry labs, maybe they do it here in biology, you get tap water, stick something in it, lights a light bulb. Maybe you did that in school. A lot of schools do it. Pretty common things. So what happens, all the things we dissolve in water basically form positive and negative ions, not including these. Depending on what we put in there, it can cause changes in this. So when we're not putting anything that impacts distribution, it ionizes basically into an H plus and an OH minus. How does that happen? Effectively, if you look back to the original model of water, remember, the electrons are being pulled more closely to the oxygen as a greater degree of what we call electronegativity. And it's imbalanced. Remember the asymmetry we talked about. Effectively, it's an intramolecular tug of war for electrons. I want those electrons. The oxygen is selfish. The oxygen is selfish. Okay? Nevertheless, which I'm worried about that little guy here. Nevertheless, periodically, one of them wins. 1 out of every 10 million of those wins and is able to grab that electron, pull it, and causing these to separate. That's what partial ionization is. It leaves an OH minus and a hydrogen ion in equal components. Anything we add to the water will impact. Some will not cause it to change it. Just be a bunch of salts dissolved in water and it'll be electrically. In general, that's what happens in our bodies. But in general, in our bodies, it's a little bit different because our pH biologically in our bloodstream, which mirrors where it is everywhere else, is not 7. We're not entirely neutral. We're slightly alkaline because of the preponderance of calcium salts, I would think probably predominate, sodium and potassium. There's enough salts in there and mineral content, and that throws it a little bit more to the alkaline side. So the range for normal pH, 7.35 to 7.45. And if somebody said to you 7.4, that would be accurate. Okay? There's a range. If your pH goes to 7.33, you're in acidosis, you're going to end up in us. That's right. That's the whole idea, is to understand that anything we put in can alter that pH. When it does so, a little change is a big number because these are powers of 10. It's like the Richter scale. If you have an earthquake that's 6.8, and all of a sudden it goes to 6.9, that's the power of 10. It's a significant change in the amount of destructive capability. If it goes to 7 or 7.1, it can level a city, cause a tsunami, whatever. It's all about where it occurs and those subtle changes. So you can't look at the number and say, oh, that's not going to make a big deal. It depends on where it's located as well. So that's when we're talking. We have pH. You ingest something we do all the time. coffee's got that pH coffee to you, and I have a thing there in my travel mug that's there. That's a pH of 10 to the minus fifth. By the same token, it flips this because they always balance out a total of 14. This becomes 9. So, I mean, if you're a chemistry major, questions come in both pH, percent of hydrogen ion concentration, pOH. For our purposes in this class, everything is defined in pH. So how come it's so forgiving? How come you and I, okay, when I have coffee, when you have coffee or a drink that has a degree of acidity, and we eat a lot of things that have a certain amount of acidity to them, as you will see, why is all of a sudden we're not becoming acidotic? Because we have mechanisms that we'll get to here, buffers, FFER, that keep that balance down. So anything we add to the water is going to create an alteration, some of them very dramatic. When it causes more protons from those water molecules, induces them to release the hydrogen and let the oxygen win, we call them anions. Causes more of those protons to be held onto, and call them bases or alkaline. When you have, like we have at home, like a Brita or a pure water filter, that thing you stick into that pitcher, effectively you're acidifying the water. You're doing it indirectly. You're taking out some of those minerals that are making it alkaline, and water that's a little more acidic is a little better tasting to us. It's a little sweeter to us. That's all you're doing is it has something called an ion exchange resin column. It's got those little black flakes in there. Those are carbon. Okay. So it's not mystery. It's very useful. I mean, most of the time with all the stuff they have to put in the water to make it city water for us to be able to drink it, it requires there's a fair amount of chemicals and additives that go in to make it safe. Now we can try to remove some of those that are there. So salts we call electrolytes because they can conduct electrical currents. That's what I was talking about before. And they're so, you're just going to hear endlessly about how important they are. Very, very. When we get to the cell, you're going to see sodium and potassium dramatically accounting for something called the resting membrane potential of your cells. That's everything. That's the foundation of why nerves and muscles work. So it's all about homeostasis. Salt, all the time. We used to, big players, sodium, chloride, potassium. Enormous players, as you will see in that membrane potential. Bones, calcium carbonate, calcium phosphate, part of it. Potassium chloride, another one. So these have a common there. They're all different. And they all have vital roles that are there. And it's just to give you an idea of what salts are in general. Okay, so acid and bases, by definition, but since they're inherently charged, okay, are both easy to dissolve in water. Anything you add again to the water will force it in one direction or the other, unless it's something in a tiny amount that effectively is neutral. A little pinch of salt, whatever salt you're using at home, is not going to affect that impact. I mean, you can get pH paper, you can probably buy pH paper, try to find some in the chemistry lab. I'm sure you used it, you dipped it, held it up to this, right? Litmus paper too, chemistry. Just waiting to blow up the classroom. Never be around chemistry majors. We don't have a major in chemistry here. They're dangerous. They have little tricks to make things. We used to put things on the steps and people step on here. It's awful. Just mean. Basically, they're nerds. Pocket protector, bow tie, suspenders. That's us. I have pictures. So here are important ones. Hydrochloric acid. That's something, your stomach. That's how it kills bacteria. That's how it starts to clobber the food you eat to begin to break it down. It has a pH of about 2. That compared to neutral water, that's 10 to the 5th. That's 10,000 times more acidic. 100,000 times. I misspoke. Acidic. I mean, if you've ever, when you vomit, you get some of that acidity. It burns. That's what it does. It's acid. Okay? Acetic acid, a little bit more mild. That's vinegar. Different vinegars have different degrees of acidity. Some are a little stronger in acidity. Some are a little bit more mild in acidity. Okay? And then carbonic acid, that's that whole thing over there. We're going to get to that shortly. That's a unique kind of an acid. It's very important, not because it's strong like hydrochloric acid or somewhat strong like acetic acid. It's a very weak acid. Weak acids, as I wrote up there, weak acid, great buffer. Because buffers are just that. They're something that ionize. See the way I've drawn the arrows that are here. They hold on, they want to hold on to their proton, but under the right circumstances, they'll leave it. So what a buffer does, when you ingest things that have a lot of acidity, okay, it'll be more than happy to gobble them up and make more carbonic acid. When you have things, you ingest things that have a lot of alkalinity to balance it out, you don't give up its proton. It's a very ambivalent molecule. I'll give up a proton or not. I'll take your protons if I have to. It's a weak acid. It will hold on to its proton, but it's willing to give it up under its right circumstances. That's what makes it a great buffer. It's the most important buffer in your system. It's why when I'm drinking coffee, you're eating foods that have a lot of acidity all the time. Our blood is not like that. 70% of all the carbon dioxide you're going to blow out from your lungs travels to your lungs, dissolves in the bloodstream, and mixes. And you're going to see this equation a zillion times. You see it in respiratory, you see it in cardiovascular, you see it in urinary. It's all over the place. It's the single most important equation that really you should have to remember. Okay? And that is, we take our 2 waste products. You love this. Carbon dioxide and water. Stuff we're going to get rid of in the presence of a magical enzyme that's in the bloodstream, not in the cerebrospinal fluid. That plays a role down in respiratory. Called carbonic anhydrase, which you don't have to know yet. And with an enzyme, we put a little arrow there, and it makes this weak acid called carbonic acid. The system is called the carbonic acid buffer, and what it does, okay, it's reversible. And at this level, okay, effectively, when you draw the arrow, it means it's going to hold on to its integrity, and to some lesser extent, when needed, it will turn into a proton, a hydrogen ion, and something you heard about before, bicarbonate. One of the things we measure in what are called electrolytes in the body, we look at sodium levels, chloride levels, potassium levels, and bicarbonate. Those 4 create a very important number that we look at when we do what's called a basic metabolic panel. 2 most common blood tests that are ordered: complete blood count and basic metabolic panel. That measures electrolytes, certain enzymes, sugars, uric acid, creatinine, and BUN, which are measures of kidney function. Yeah, that's more AP2 stuff. For many of you go into clinical fields, that's stuff that you learn later on. I'm giving you the introduction. I never had a doubt Steelers are going to win. Such a liar. My wife was tempted to throw water on me after they played that failed 4th down. Yeah, look. She told me to please sit down quietly, though she did not use that language. She used a different kind of simple declarative statement, emphasizing some creative usage of certain swear words that we do not use here. Terms of endearment. I digress. So acids donate the proton, okay? Strong acids complete. There's no holding it on at all. Important acids you can see there. Bases accept. Okay, so they pick up the proton, and in doing so, because of that, it tends to cause an imbalance because it's always going to that 10 to 14. The number is the hard part to remember. It's called a negative anti-logarithm. You don't have to know that. All you have to know when it comes to pH, a big deal with pH is that the number that you see there, that's logarithmic. So when we talk about a negative anti-logarithm, all we care about is that number. So what happens as pH goes down, okay, acidity goes up. Again, it's the denominator. If that exponent goes down, basically, that becomes 100,000. We make the denominator small. We make the denominator smaller, effectively make the numerator larger. So by reducing that denominator, effectively get a larger number. It's one of those just because things. It's a little counterintuitive. So we have increasing acidity, pH lowers. We have increasing alkalinity, pH rises. However you want to remember it. We'll get to the ammonia in just a second to show you how alkaline it is. Why do we make a lot of ammonia? It's very toxic, but when we ingest a lot of proteins, as we do, ammonia is something that's created. We have to find a way of dealing with that. That's another magical use of that good old carbon dioxide. We'll get to that some other time. So here, the scale is such like that. So the pH is a negative logarithm or anti-logarithm. All you got to do is look at the end, not the negative sign, but the last number. That's for concentration, brackets. A tenfold difference, that's what I was telling you about before. So acid-base concentration. Normally, neutral is 7. Again, for our bloodstream, it's slightly more on the alkaline side. 7.35 to 7.45 is the accepted scientific range. If somebody, a test question of 7.4 is fine. They're right in the middle of it. 7 is incorrect. Okay, because we're not filled with pure water. We make, even in the lab, in micro lab, which you guys are going to have next semester, most of you will, we have in the back sink, you have a whole gizmo gadget giant thing there that makes deionized water. Well, triple deionized. So that's as close to pure water. And it's used a lot for laboratory experiments. So you can see 0.699 or 7.01 to 14. Examples. So we have a palate. We find acidity tasty. Alkalinity is bitter. Okay. So here, lemon juice, rather substantial pH, -2. That's really the same as stomach acid. Okay. It's not hydrochloric acid, but it has a real bite to it in that regard. Yet we squeeze it on dishes all the time. We call it for brightening it in cooking. A little squeeze of lemon, like that, because we have a palate for that. Our taste buds, sweet, salt, sour, bitter. In cooking, you want to get all those banging at the same time. That's what makes the dish. There's another one called umami. That's why we use things like mushrooms or soy or Worcestershire, things like that. Dish sauce, fond of that. In Asian cuisine and Thai cuisine. Okay, boom. You're bang, bang, bang. You're channeling them all up. Maybe throw a little spice in there for heat. That's what makes a dish really good. Not for everybody necessarily. So a lot of the foundation of salad dressings are what are called agrodolces, sweet and sour. They have a certain amount of sweetness, honey, sugar, mixed with whatever vinegar, and they add stuff to it. Pretty straightforward stuff. So here, blood, 7.4. Milk, slightly acidic. Coffee, more acidic. Look what we do when we want to make coffee a little bit easier to tolerate. We add some dairy to it. We change it for the most part. If you ask me about almond and soy milk, I don't know. We use a lot of almond milk at home as well as regular stuff. And here's wine. As you can see, increasing amount of acidity. It's sort of like the thing. We use that a lot for acid or for like a certain amount of fruit or smoke, whatever. People who appreciate wine, I do not. Most of the stuff I use for cooking. And you can see hydrochloric acid, effectively it all ionizes all the way down to zero. Stomach acid, a little bit less intense. And you see all the stuff you would never want to ingest. Okay, egg whites, I'll buy that. We're good with that. Okay, household bleach, yeah. Ammonia, are you kidding me? That's the kind of stuff that are nightmare scenarios where people are trying to do themselves in that you see in an emergency room. And then you're just trying to keep hope that they can get enough healing that they can still swallow things normally. Okay, I really don't care about neutralization reactions. It's something we did in high school. We took sodium hydroxide, hydrochloric acid, the extremes of alkalinity and acidity. You put two clear liquids together. Magically, you carefully, might I add, and then you heated them to boiling. You boiled off the water, and you found you were left with salt at the bottom. I mean, it's a classic reaction. Doesn't tell me a whole lot for our class. Here's the buffer, the important nugget about buffers. Just like I said to you before, they resist the large swings. And we have calcium provides one, as you will learn. Proteins provide one because they have the capacity to either absorb or give off protons as necessary. They have hydrogen ions and protons interchangeably. And weak acids, the ones that slightly dissociate, make great buffers. This is the most important one of all, the carbonic acid bicarbonate system. All over. You're going to see that when you start talking about, when you hear about somebody who has problems, they have to take things like Prilosec or protonic agents in their stomach. And you're all going to know somebody who has stomach acid problems. We utilize that. So important, okay, to understand how that mechanism works. And that's well in AP2. It plays a significant role in respiratory. Because it's the reverse of that that allows us to expel that carbon dioxide. There's so much that goes on with it down the road. I do it in a very much, when I do my advanced phys course next term, we go into it at great length, but I want you to be familiar with it. And again, the big deal that we're going to get to down the road, or you'll certainly get to in respiratory at AP2, cerebrospinal fluid does not have that enzyme. That's why it plays a pivotal role. It's different in things that force you to breathe. The mistake is everybody talks about, oh, there's not enough oxygen. I have to get oxygen. That's not the thing that makes you breathe. It's carbon dioxide. All the time, all day long. So enzymes, very narrow range. Okay, look at this. We in the old days, we didn't have those magical things you stuck on the finger to be able to tell what their O2 saturation was. Okay, we did arterial sticks in the air. If the person had a pulse, we stuck a needle in there with a syringe. We sent it to the lab. Half an hour later, we got the blood gases back, arterial blood gases. So we had an idea what the pH is or the oxygen content. So look at that. Arterial pH of less than 6.85. They're not making it. Here, bad predictor of outcome. Now we get into the true organic chemistry part of the program. There's a goodly little nugget of time to talk about the exceptions, carbon dioxide and carbon monoxide. The fact that never use never. There's not a whole lot of alwayses and nevers. It does occasionally gain or lose them, but we're not going to go into that or criticize. It mostly shares electrons. Yes, they're covalent bonds. Yes, it's what our foundation. We're a carbon-based life form. Okay, they are these components, and they're composed of, with the exception of lipids, beg your pardon, small molecules and larger molecules. We call macromolecules. Back to that hierarchy, very first lecture. So you'll see those as we will come to them. Again, with the exception of the lipids, the fats, you have monomers, the small repeat unit. You have typically a small molecule. When we get to carbs, principally it's glucose. So glucose is a small molecule. When it chains together in different ways, we have three that we become intimately acquainted with and formal design. Animals, including ourselves, chains of glucose that we can use rapidly us, only two places, liver, skeletal muscle. Well, glycogen, it's like our emergency sugar supply. Mention that. You ingest animals like meat, chicken, meat, beef, any source. You're going to ingest a certain amount. Most of the way we get, and these, when we talk about glycogen starch, these are so-called complex carbohydrate complexes. We ask them out of our diet, most people's diet, versus our complex carbohydrates. Starches come from plants. We can break both of these down. Glycogen from animals, starches from plants is how they store carbohydrates. They have a much greater capacity. Plants also have structural carbohydrates called cellulose. That we do not have the capacity to break. We utilize it in its form. Okay, that's basically cell walls, it's plant structural material. And like a cow has the enzymes to break that down into glucose. It has to do with how it's assembled structurally. There's chains and there's different cross branching and stuff like that. That's in a biochemistry course. Our idea is, hey, cellulose we can't use, but we find ways to use it. We can't use it as an energy source. So we hear about somebody carbohydrate loading for sport. Things have a lot of carbs. So pasta, for instance, like that. So, so we look at monomers. They're not always the same thing. Amino acids are a monomer that makes protein. There's 20 of them. They're structurally similar, but they're not identical. And they impart different properties. And we'll spend a lot of time with that. And here's that nugget about dehydration, synthesis, and hydrolysis. Take away water. Some authors call that condensation, like you had in your car this morning. Dampness on there, on the windows, condensation, moisture coming out, dehydration, synthesis, and hydrolysis. Here's the classic example of it. These are monomers. Most biological molecules of those building blocks of fats or lipids, carbs, amino acids for proteins, nucleotides for DNA and RNA, they all have free OH groups sticking out. We find two of them that are in close proximity, has to do with the way they're bonded. By the way, we pull out of water and we link them together by a covalent bond. Again, a bond that has stored a fair amount of energy. Whether or not it's nonpolar, most of these are nonpolar, some of them have degrees of polarity. I'll mention those when that's relevant. That's there. We can take the same thing and link them together, or we can reverse the reaction and add water and break them apart, return them to their initial state. Okay. So again, that's the idea, both directions. An equilibrium frequently exists. You'll see that in cells. Okay. When you have something, typically it creates an equilibrium. Things don't just stop moving around. They don't just stop forming or stop breaking down. They create an equilibrium of as many things are being stored as are broken down. We'll talk about equilibriums a lot. Another term is steady states. Things are always, if things stop moving, you're not alive. Not a good thing. Here's a classic example. This is the first one we learn about. Even though it can go in both directions, it's basically that. Here we have two monomers. Okay, these are 6 carbon sugars. They have different structural appearance. They are the same chemical, as you will see very, very shortly. Glucose and fructose together. What happens is, take away water, you form table sugar, sucrose. On the same token, if we put sugar in water, even though it doesn't dissolve as fast as salt, it will dissolve, okay? We can reverse it and have water that contains glucose and fructose. We principally utilize glucose. Our brain can only utilize glucose as an energy source. In men, the only energy source a sperm can have to move around is fructose. Okay? But we can change things from one to another. Because even though they don't appear the same structurally, we have enzymes that flip them in such a way. So biologically, we need bless you, to utilize the fructose, oh, you're in trouble. And so we usually use it in my house. We do, bless you to all. We're good to go. You can flip them to glucose or flip them to fructose if that's the appropriate need at that particular time. There's different things for different equations. And here's the sucrose. Okay, those are, as you're going to see, small still. These are called monosaccharides, one sugar, and this is a disaccharide. They're both considered small molecules. Only those ones up there, the glycogen, the starch, and the cellulose, long chains, are considered macromolecules or complex carbohydrates. These would be simple. Bless you. Oh, that wasn't a sneeze. Shocked I'm not coughing. I was vocal yesterday. So carbs include sugars and starches. By that, CHO, 2-to-1 ratio, that's what makes them carbohydrates. We did that before. Monosaccharides, monomers, small sugars, disaccharides too, both small, poly, complex carbohydrates, many. This is the same formula I mentioned in passing before. Water and carbon in equal numbers. That's subscript of N. The ones, you'll see we use 3 and 7 sometimes. 3 we'll talk about, 7 we won't. But the ones that, and we use the suffix "-ose", pent, like a pentagon, 5 sides. Pentose, ribose, and deoxyribose, really the difference between DNA and RNA, right there. And hexose, all the ones you saw before were hexoses. Glucose, fructose, and one that's in milk called galactose. And that, like lactose, kind of gives you an idea of where it's a component of the very famous lactose that we will get to. And here they are. You can see glucose, fructose. The oddball with fructose, you see these are hexagonal in shape. This is pentagonal. Don't have to know the shapes. Here the carbon is sticking out this way. Here's another one where the carbon's sticking out this way. We got 6 sides. But inside our bodies, we can change them about so they all can become glucose if necessary. And here's deoxyribose and ribose. They're pentagonal in shape. And the whole difference, this one has an OH, this one doesn't. Okay, this one has an H. So it's lost in oxygen, hence deoxyribose. And that tiny, tiny little change changes it from a linear molecule to the very famous double helix. So a tiny change can impact shape dramatically, almost change it into something that really is the inherent part of our life. I'll leave you with that. We'll pick up here. Again, I'm not going to be here on Friday. It's most likely going to send you a recorded lecture. I am going to, they asked me the other class, I'm going to try to, as soon as I get back to my office, I'm going to try to get study guides out for test 1. I got to check with Dr. Robbins, who I haven't seen yesterday, to affirm the date. Okay, all good? Thank you very much. Enjoy the rest of your day. Nice talking to you.